All right, guys, so this is going to be what we call lesson 6. It'll be your lesson 2 for Friday, May 21st, okay? So this morning, you guys would have seen we dealt with these new five new equations, right? That allowed us to take into consideration when an object is accelerating, okay? And what we would have saw this morning is the acceleration kind of questions that we would have seen would have typically been in what we would call kind of maybe in the horizontal direction, okay, in the x direction, okay. Now the magic thing about those equations is that they apply to objects that happen to be have their motion in the y direction as well, right? Okay, so this morning we would have seen objects traveling like a car, accelerating on the ground, things like this in the x direction, right? Now this afternoon, you're just going to get more practice working with these equations because this is virtually identical with the exception that now the objects are traveling in the y direction, right? And a couple interesting phenomenon happen because of that, and there'll be a few supplementary videos that you guys can watch that I think are kind of cool. But if we just have a look at this initial paragraph here, it's going to talk about objects in free fall that are accelerating due to gravity. It's not accelerating because the car is accelerating, right? Because the motor is doing the work or anything like that. Gravity is causing the object to fall, okay, and accelerate, right? So it gets faster and faster and faster until a certain point, okay, which you'll learn about today as well. Okay, so acceleration of gravity is the acceleration that occurs when an object is allowed to fall freely, okay, and the symbol for that acceleration is the letter G, okay, and so we saw this a little bit yesterday, okay. You would have seen what we denoted with the dimensional analysis. I told you what G was, okay, and then we would see it today. So physicists have determined the average value of G measured very close to the Earth's surface is 9.8 meters per second squared, okay? So that's you'll never forget this, really. The more physics, it's never going to go away. You need that. But different places on Earth, ironically, have different values for G. Very subtle, but they do. And some of that has to do with the elevation, right, which we see here. So it was something interesting, and I included this paragraph because I thought this little example here was interesting. The value of G in Mexico City is slightly but measurably lower than the average of 9.8 meters per second squared, right? And this is because the city has a very high elevation and therefore is farther from the Earth's center, okay? So ultimately what we'll learn in this course as well is that to dictate or figure out where that 9.8 came from, it takes into consideration how far you are from the center of the Earth, okay? And so there was some interesting effects on these 1968 Summer Olympics, right? Which people were breaking records all over the place, like because they're essentially feeling less gravity, and so they're traveling further, right? So many high jump, long jump, pole vaulter records were broken during these games, right? Which is kind of cool. I just thought that was cool, and I thought I'd include it, right? But the acceleration due to gravity of an object near the Earth's surface will be about 9.8 meters per second squared, only if it's dropped in a vacuum, okay? And this type of motion, so if there's no air, okay, basically. This type of motion is referred to as free fall, which is acceleration that occurs when there's no air resistance, okay? So what ends up happening is you're going to drop something. In reality, for your purposes, we're not going to have a numerical value that's going to affect your homework questions, right, for wind resistance. So, but in reality, and you'll see this in a couple videos today that I found, an object free falling is experiencing acceleration of negative 9.8 meters per second squared, right? Negative being in the downward direction, right? But in real life, like when you go free falling, there is the force of the air pushing back on you, right? And so this number, because there's a force opposing this acceleration, it's a little bit slower. But for your purposes, for what we're going to do in introductory physics, right, we're going to ignore, you'll see a lot of the questions will say wind resistance negligible or something like that, right? So anyway, it's basically the same stuff from this morning. I'm going to run you through a couple examples, okay? But the key difference this afternoon is that objects are traveling in just a different axes, right? They're traveling in a y direction instead of the x. We can still use the same 5 kinematic equations that I showed you this morning, okay? And the approach to solving these questions is the exact same, right? It's actually maybe even easier because you know that acceleration is 9.8 meters per second down, per second squared down, okay? There's no deciphering what the acceleration is in these questions, okay? Okay. So this is just reiterating everything I just said, okay, just in text. So what I want to do is just run you through 2 examples, and then that'll be it. And then I'll have some videos posted for you guys to watch as well, okay? So what we want to do here, we want to determine the amount of time it takes for an object to hit the ground, okay? So a flower pot is knocked from a window, okay, and the window ledge is 10 meters above the ground, okay? And there's no air resistance. Okay, see, there you go. You see that right away. How long does it take the flower pot to reach the ground? Okay. So, what I like to do, right? I like to always, and we saw this a little bit yesterday too, or maybe it was Monday. With this grass method, I wouldn't necessarily I don't explicitly do this anymore. You guys might choose to do that, where you say, okay, what are my givens? Right? You can say, okay, well, right off the bat, I know that the acceleration, remember acceleration, which we'll see this morning as well, or we would have seen yesterday, acceleration is a vector, right? It has a magnitude, and it will have a direction as well, right? In this case, acceleration is acting downward, right? So you could have negative 9.8 meters per second squared. Okay. So I like to write down all the givens, right? And even sometimes when I like drawing pictures too, right? Because I think the pictures help sometimes, right? So here's my flower pot, and it gets knocked off the edge, and it falls straight down. Right? And our question is, how long does it take to hit the ground? Right? So let's just run through these things, right? So we know the givens. We know that the acceleration is going to be 9.8 meters per second squared down, right? And we know that the change in displacement, and this will come up a couple of times too, right? Look, the D final relative to D initial, right, was like, here we got 0 meters down here on the ground, right? But initially we have 10 meters. And so when I find my change in height, or we're going to see, or distance, we're going to find change in D is going to equal D final minus D initial, right? And what you're going to see, and this will come up a couple times because it ends up messing with the signs a little bit sometimes, right? But this is why it is the way it is, right? So D final is going to be 0 minus 10. And so what you're going to get, you're going to say, okay, well, the delta D value, or the change in distance or change in height, what you'll see sometimes is maybe we might use change in height for the vertical questions, right? As opposed to delta D, but both mean the same thing. Relative to the equation, you're going to get negative 10 meters, which you could say 10 meters down. Right? Same thing here. You could say this is negative 9.8 meters per second squared, which is, I think I set up above too. Okay. So here's two of your values so far, where they've come from anyway. You could say one of them is this, and one of them would be this. Okay. For A and delta D. You also know one other thing, and we would have seen some of this morning too. We know the initial velocity of the flower pot. It was 0 meters per second, right? And so there's one thing you're looking for, right? It's what is the time value, right? How long does this take? The change in time, right? And so we just need to select an equation that's going to solve the question for us, right? So you look at what you're given and what it is you're looking for, and one of those 5 equations should do the trick for you, right? And you might see, if I was just looking at them, I might pick well, we're kind of stuck here, right? Two things here going on, right? If I were to try and pick, let's say, for instance, remember I'm trying to solve for t. Most of these have, oh, there's, okay, I could pick this one actually. I could pick this one. The nice thing about these questions is the longer you stare at them, the better and better one looks over relative to the others. So you could probably use this one here. Delta D equals V1t, or V initial t, plus 1/2 AT squared. The reason why I chose this one, because if I go through here and I look, I know what the acceleration is. I know what delta D is. I know what V1 is. The only thing I don't know is T. Now you might be looking at that and going, oh boy, this looks ugly, right? Well, and it does kind of, but the nice thing is V initial is 0, right? So if I were to plug in 0 and I multiplied by, it doesn't matter what I multiply by, T, doesn't matter what T is, it's gonna be 0, right? And so this initial term actually cancels out. And now you can plug in your information, right? Well, you know the change in displacement is going to be negative 10 meters is equal to 1/2 of negative 9.8, right, t squared. Now, this still looks a little bit ugly, right? And I'll show you how to deal with that in a sec. But we can now do some like math on this. We know what half of 9.8 is, right? So we're going to get negative 10 meters is equal to negative 4.9 t squared. Right? So you say, okay, well, I'll divide both sides by negative 4.9. I don't really need the meter in there. You could. Just clutters things sometimes. Okay, now the 4.9s and negative 4.9s, they're going to cancel each other, and you're going to be left with t squared is equal to 10 divided by 4.9. So if I type that into my calculator, that's all you're doing. You're going to say, okay, well, or negative 10 divided by negative 4.9. You remember that the negatives are going to cancel here, right? And turn into positives. So you can just do 10 divided by 4.9. You'll see that that should be 2.04, right? But I don't have t by itself, right? I have a t squared. You guys would have learned in grade 10 to solve for the t value. In this particular instance, we could square root, right? And we learned this in some of the math concept review from the day 1 too, right? Could square root to get rid of a square. That's the opposite, right? And so, but what you do to one side, you have to do to the other. And so t is going to equal the square root of 2.04, which is going to equal, if I square root that number, I get 1.42. Okay. Okay, and so this is how long it takes for the object to hit the ground. Okay. I think that's it actually. I could very well ask you as well now, as an additional part of this question. Maybe I'll shrink this down. I could say, okay, well that's good. You know how long this motion takes, right? Now my question is, okay, well, what's the velocity when the flower pot hits the ground, right? And you could select a different equation, right? You could pick something like v2 is equal to v1. Sorry. I'll try to keep it consistent. V final, v initial, plus a delta t. What you'll see is I'll probably end up doing this. They're interchangeable. Vi is v initial, or v1, and vf would be v2. Okay, you'll probably see me do that in solutions, or you might see somebody else's solutions, or Khan Academy or something to do that, right? Just so you're aware. Same thing. Okay, so I could very well ask you this. Now that you know what the time is, you can now take what this time is and plug it in here, and you can tell me what would the final velocity be just before it hits the ground, right? Okay, so we just got one more question here just to get some practice. Oh, never mind, I did ask you it. What is the final velocity of the flower pot from example 1? Well, we get to do it now. Okay, so I'm going to use that equation. V final is equal to V1, I'm mixing them now, Vi plus a delta t. You know the change in time is 1.42, so you're just going to plug in your values, right? You still know, this hasn't changed, so you still know the initial velocity is 0, right? So you say, okay, well, that's 0, so V final is going to be equal to a delta t. Right, so V final is equal to oh, I know why. Okay, so negative 9.8 multiplied by 1.42. Okay, if you guys are wondering, the same wondering I'm having, why is this number negative? How does that relate to my answer? I'm going to show you that in a second. Okay, in case you're burning with a question. Okay, but you just do the math on that. So I'm just going to find my calculator. Right, and we're going to go, we just need to take 9.8 and multiply it by 1.42, right? Sorry, negative 9.8. We're going to see that we get negative 13.9 meters per second. All right, you're saying, oh, how does this make any sense? Like, right? Remember, final velocity. Velocity needs to have a magnitude and direction. Right? And so you're going to have to say, okay, well, therefore my final velocity, or the pot's final velocity, not my velocity, oh my goodness, 13.9 meters per second down. Okay, that's what the negative means. The negative implies that it's going down, right? And that's it. So you can see how I can give you questions, Sometimes I can scaffold them nicely for you. Scaffolding being like spell them out in like a part 1, like a part A, part B. Sometimes I can be mean and say, oh, don't solve, like I just won't say solve for the time, so you don't know that you need to do all of this work, right? I'll just say, what's the final velocity of the flower pot? And so sometimes you're like, oh, well, there's no equation. Like I don't know all of the information in one of the 5 equations, in which instance you're going to have to do some precursor work to figure out what time is so that you can use one of the equations. It doesn't have to be time either. It could be another variable. Okay? So sometimes you guys are getting started here. I'll be nice, right? And scaffold these for you so that here's part A. Now that you have the time, now you can plug the time into the question. Okay, but there are instances where you guys are, this isn't going to be scaffolded nicely for you. You're just going to say, what's the final velocity? You're going to have to do some, oh, I need the time in order to do this, or I need delta D in order to do this sort of thing, just based on what they've given you. Okay, so you got to look, that's sometimes the importance of having this list up here, right, of things that you know and things that you do not know, because that sometimes puts you in a direction. If I were to look at that, and this question asked me, like if I included the fact that I didn't know what V final was, or V2, I might be looking at all my givens and looking at, okay, well, I'm going to have to solve for time first in order to get to final velocity. Okay, and so that the givens and the picture, that is the physics of the question. Okay, as well as selecting the equation. But from that point forward, it's all math, right? So everything kind of in the pink is physics, setting up a problem, representing a problem with a picture, finding what you need, selecting a tool. That's all physics. Okay, so let's just do one more. We'll run you through this one, and then that'll be it. Okay, so what we've got here is we have somebody who, like a tennis player. If you guys have ever seen a tennis player throw a ball up in the air, and they strike it at the top, sort of thing, right? The top of its motion. But the question here is like, we want to know how long it takes to get to its maximum height, right? So a tennis ball is thrown straight up in the air. It leaves the person's hand with a velocity of 3 meters per second, right? It's positive. It's leaving his hand with a positive velocity, right? And I always just I always stick to a typical coordinate system where up is positive, just so you can do whatever you want, but everything has to follow that coordinate system, right? So we want to know how long it takes for the ball to reach its maximum height. Well, this one's kind of nice because it's already drawn the picture for you, so you can kind of visually represent in your head what's going on. But beside, we can write down the things that we know and the things that we don't. Right? Well, givens. What are we given? Well, we know that the ball left the person's hand with an initial velocity of 3 meters per second, right? So I know VI is going to be 3 meters per second. And that's going to be pointed up, right? Or in the positive direction. Okay, we also know the acceleration due to gravity. It's going to be 9.8 meters per second down. Right? We can make it negative, because in the downward direction, that's all negative stuff, right? And we also know there's one key thing, right? And you guys would have seen this in your math course, and we talked about it yesterday, actually, too. When I throw a ball up and it reaches its maximum height, we saw this in a velocity time graph, I think. VF equals 0. Right? It stops. It stops in that. So whenever you're talking about the maximum height of something, right? There is a split instant in time where the object reaches a zero velocity and turns around, right? It's in that turning around that the object has reached that final velocity of zero. Okay, so you can include in your list of knowns. You know the final velocity for what we're interested in, the maximum height. The final velocity at the maximum height is 0 meters per second. Okay, now you're just going to look at, okay, well, what is it that I'm looking for? Well, I'm looking for delta t. That's unknown. I don't know what it is. So you're looking at your lists of knowns and unknowns, and you're trying to pick an equation that's going to best serve you. Okay, if I'm looking at what I've got in front of me, one of those 5 fits that nicely based on what I'm given. I would say I could pick V final is equal to V initial. And if you guys want, like, if you don't like the F and I's, I'm totally impartial to, like, I don't really care. V1. I prefer V1, V2. I keep stumbling, but it's completely up to you guys. V initial plus a delta t. That would be the one I'd pick. Right? This fits the information that I'm given perfectly. Right? So you can plug in the fact that VF is 0. You know that. Well, VI was 3.0 meters per second. We don't need the units. You can include the units, but you don't need to. That's what dimensional analysis is for, right? Plus, now here's the catch. Acceleration is pointing in the downward direction. So I'm going to say negative 9.8 times delta t. Okay? You're just going to solve for delta t. So you're going to say, okay, going to create a 0 pair here. This is like the math review. I'm just going to go -3. What I do to one side, I got to do to the other. So we get minus 3.0 is equal to negative 9.8 multiplied by delta t. Okay? Now, you can say, okay, well, I just got to get delta t by itself. Well, the 9.8 is attached with multiplication, so I can divide both sides by negative 9.8. And delta t is going to equal almost 0.3, but not quite. Let's see. 3, and again, same reason I'm saying 3, but it's -3, but you have 2 negatives there, so they're going to cancel. 3 divided by 9.8. 0.306 or 31. Oh, that looks like 5 seconds. Okay, so therefore it takes 0.31 seconds for the ball to reach okay. So that's it, guys. I could also ask, based on that information, I could ask any number of things, actually, right? We could also say, like, oh, maybe I don't want the time. Maybe I want how high. What is delta D? Right? How high did the ball go? Right? You could just pick an equation for that. The equation you could pick could be this one. Right? So I could ask you anything about these, the motion of an object, really. You guys could have that's what's cool about these kinematic equations, right? You could pick, in this instance, you could say, oh, maybe I'm going to pick, I don't have an equation explicitly for delta D that'll work here, but you could pick this equation, VF squared is equal to VI squared plus 2A delta D. You could do all the back solving, right? You could say, okay, well, if I want delta D by itself, I could say VF squared minus VI squared is equal to 2A delta D. If I wanted delta D by itself, I could divide both sides by 2a. And I could say, okay, well, delta D is equal to Vf squared minus Vi squared divided by 2a. And you would get a number for how high the ball actually traveled. Okay. So what's cool about these is you have 5 equations and they do all sorts of different things based on different information that's given to you. And the only way that it really gets harder than this is if I don't scaffold the question for you and I say, okay, well, I could pick questions that kind of you have to do an intermittent step in order to figure out what your answer is, right? There's sometimes do 2 steps questions, and we saw that this morning, right? And that's it. That's going to be a pretty common theme, okay? So because you're going to have to do, this is where things start to get a little bit interesting, right? It's got to do some connections, right? It's good for you. Your brain's going to grow, okay? So that's it. I'll post the supplementary videos that go with this that I think are kind of cool that fit this concept. And it talks about what role air has, air resistance on the motion of an object, and I think there's a cool some cool videos that I think you guys should watch. Okay, I'll include them. Okay, so that's that. There's some problems associated with acceleration due to gravity or kinematic problems specific to gravity or free fall that are in section 1.5 or 1.6, sorry. So I've posted those and I posted the textbook and you guys have answers to that stuff. Okay, so just in case you need to see it. Okay, so that'll be it for today. Hopefully everybody has a good weekend, and it's a long weekend, so I won't see everybody until Tuesday. And I've posted formative 1 as well. Okay, so you guys have that to work on. Okay, so let me know if you have any questions, and have a good weekend.